Welcome to Lesson 4, Learn C Programming on the Raspberry Pi. Today I won't be showing you the actual Raspberry Pi I'm working on, but it's the same one I've been using for all the previous 3 lessons. It's a Raspberry Pi Model A. So the first thing I'm going to do is bring up a terminal and connect to the Pi. I already have it powered on. And remember, the password is Raspberry. Okay. So in lesson 3, I'll show you where we left off. We left off with this program called exponent.c, so let's start Genie to have a look at it. I start Genie in the background, wait a bit for it to come up. Okay, there it is. And recall that in this example, we were using the POWF function to compute the power of 2 floats. So x to the power of y. In our example here, it's 2 to the power of 5. Should give us the value of 32. And we're also using the floating point square root function to get the result, the floating point square root of 32, and we print them out. And we're also using the printf function. So if you look at what we're doing, we have the main function, the powf function, the square root f function, and the printf function. So we're really working with 4 different functions here. Okay, and I think the last day I showed you, let me move this screen over here, I showed you how to do a compilation using the GCC command. And I also mentioned that since we're using the math library, I had to include the math library on my compile command, on my GCC command. So I said -l library m. And just to refresh your memory, I also could include the C library, but recall that the C library is included by default, so it's not necessary for me to have this on the command line. Well, I'll leave it there anyway. So this will compile, and then I can execute exponent, and there you have the answer. Another interesting Linux command is the LDD command. LDD, and you see it says print shared library dependencies. So basically what this command does, it shows you which libraries your code is actually using. So what I'll do is I'll say LDD on exponent, and if you look at, that's our code. If you look at it, you can see that I am using the math library, and I am using the C library. So the math library is being used for the square root function and for the power function, while the C library is being used for the printf function. Okay. I also couldn't find, in the last lesson, I couldn't find where the math library was located, but now you can actually see the directory that contains the math library. In fact, it's the same directory that contains the C library. So let's go to that directory. And I'll just look at the static version. This is the static C library. Oops. Let's have a look at the non-static one. Dot star. Hang on a second here. So you can see lib c.so.6 is actually a link to this one here. So if I look at that one, just want to get an idea here. You can see that library is what is that? 1,242,776 bytes long. Okay. Now this is the dynamic version of the library, so we call it a shared object, SO. Those of you who are from the Windows world call your dynamic libraries DLLs. So in Windows you'd see something like libc.dll, probably more like libc.dll since Windows tends to capitalize everything for some reason. Anyway, there's also a static version of the library if you want to do a static link, and I will find that for us using the locate command. libc.a, and I do have it here in user lib. So let me change directory to here, and if I do an ls-l on libc.a, you can see it's about 3 million bytes. I put an H in here to say human readable form. You see it's 3.2 megabytes. In fact, I can look at all of the functions using the AR command, this archive command. I can say ART libc.a, and that will show us all of the functions in there. In fact, I can count them using the word count number of lines, and you can see in the C library I have 1,515 functions. I could also count the ones in the math library. And in the math library I have 290 functions. So the math library plus the C library combined will give us probably 1,800 different functions. I could also do a search, a grep, for sqrt, and inside the math library you can see I have lots of different square root functions, different codes, executable codes. Okay, well, this is probably getting a little too deep for us, so let's just go back to lessons. And what I'll do is I'll make a new directory called lesson04. -04. Lesson -04. Okay, so today's example I'll put into this directory. Okay, so far in our lessons we've just been learning how to use functions that are available to us in the C library, in the math library, but the only function we've created is the function main. But we are allowed to make up our own functions, and we can give them any names we want. So let's start with a new program. Let me remove this guy here. I'll start with a new one, and I'll say I'm just going to put this in because I want to use the printf function, so I include this header file. And now I have main. Remember, it's always necessary to have main because that's the entry point for the program. That's where your program starts execution. So what I'm going to do here is I'll just put in a number. Let's say I want to do my own power function. So I'll say int, well, let's use float. Float, say I want to go x equals 2.0, and I would like float y equals 5.0. So remember, we did 2 to the power of 5 was 32. Excuse me, we used the powf function to compute that. But what we'll do is we'll make our own function to compute it, and I'll just call it my powf, my powf, and I will pass it x and y. But before that, I want the result. I'll just call it r. I want the result r to be the value of the my powf function, and then I want to printf, and I'll just say %f to the power of %f is %f/n, quote, comma, x, comma, y, comma, r. Okay, remember that these %f, these are just placeholders. The first %f is a placeholder for the value of x. The second %f is a placeholder for %y. And the third %f here is a placeholder for r. So in between the double quotes, that's your format string. That's your format string. Okay. And once we're done with that, we'll just return to the operating system. And I'll just call this, I'll save this file, save as, and I'll save it. I want to go to lesson 4. And I'll just call it mypow.c. I'll just say save it. And if I look now in my directory, I should see mypow.c. So I'm not using any other functions in here, except printf is from the C library. But now I need to define my own function called mypowf. So I'll just add that in here. Float mypowf float well, let's just call them the same names for now. Float x, comma, float y. Now what we're going to do is we're just going to take x and we're going to multiply it by itself y times. And that'll give us x to the power of y. So I'll just say, I'll put a comment in here. Say multiply x by itself y times. Okay, so that's what I'd like to do in my powf function. So in order to do that, I'm going to need a loop. Now we haven't done loops yet, but I'll introduce you to the for loop right now. So first I need a counter. Well, actually I do have a counter that this is only going to work, I guess, for integer numbers, but that's okay. So I'll say int count is equal to y. Now what this is going to do is it's going to create a variable called count, which is an integer, and assign it a value y. Well, y is a float number, which means that the integer count will be truncated. So if y is 2.0, then count will be 2. If y is 2.1, count will be 2. If y is 2.2, count will still be 2. So this little function I'm writing should only be valid, should only work for whole numbers. But that's okay. So now we're going to do a loop. Good. Oops. I need another integer here. I. For I equals 0. I is less than count. I plus plus. And we'll say, now we need the total here. We also need a float result equals 0. So we'll say r is equal to r, let's see, times x. I think that's what it's going to be. Well, I think we might have to go here, change that to 1, and we'll say less than or equal to count. I hope I don't make a mess of this because I'm doing this off the top of my head. And so the first time we go through, R will be 2. Then 2 times 2 will give us 4. Then 4 times 2 will give us 8, and it should work out. So that's our little loop. And then we can just say return R. So you notice our return value up here is a float. We're returning R, which is the basically the multiplication of all of those 2's. Okay. Well, one thing we've left out here is that since main here does not know anything about POW or my POW F, it has to be told that before it hits this line. So we need to add this prototype up here. This way main knows that my POW F is basically returning a float, and it takes 2 float arguments. Well, I don't know. Let's try saving this guy. Let's try compiling him. Project build, see what happens. Compiled successfully. Well, let's see if we're going to get the right answer by actually executing it. So it says 2 to the power of 5 is 0. Well, obviously we have a problem. And that's because we initialized R down here to 0 when we should have probably initialized it to 1. So let's try this again. We'll try build again, try and execute again, and see what kind of answer we get this time. And this time we get the correct answer. 2 to the power of 5 is 32. Okay, so looking at this whole program, I know it's a lot to take in right now just for lesson number 4, because we haven't talked before about making your own functions, but and we haven't talked before about making loops or repetitions of code. But that's okay, because we'll be doing a lot of this in the future. But the important thing here is that we made our own function. This function, myPowF, it's not part of the C library, it's not part of the math library. It belongs to us. We created it, and here it is right here. And we don't have this function defined inside of a header file. So we have to tell the compiler that this is the definition of that function. So you notice we give a name of the function here. We give what the function returns. You notice down here it's returning a float. And it's taking 2 arguments that are both floats. So when we call it, we're calling it with 2 float arguments. Okay. Now if I wanted to, instead of putting this definition up here, what I could have done, in order to make main aware of myPowF, I could have taken all of myPowF and I could have just put it up here. ahead like that. Let me just remove it from down here. So in this case now, you can see that my program starts at main, and the compiler actually compiles top to bottom like this. So it is perfectly aware of my POW-F by the time it gets to this line, because the compiler has already scanned all of this information. But the normal rule, or maybe not so much as a rule, but I guess what programmers usually do is they put main at the top. And when you put main at the top, then all of your functions go at the bottom, which means all of your functions need to have definitions up here just after that include line. Well, let's try this anyway if I save it. And this time I'll try compiling it on the command line. And I call this mypow.c -o mypow. And you see it compiles correctly, and that's because the function mypow-f comes ahead, or the definition of it comes ahead of its use. So this is considered the entire definition of the function, and this is where I use it. And if I execute it, mypow, and I get the right answer. Okay, so once again, I'll just take this code here and I'll move it to the bottom, and that way I'll have main coming first, and I just put my definition here, just that one line, just called the prototype. That way, by the time when the compiler compiles, it compiles from the top to the bottom. When it hits the mypow function, it already knows all about it. It knows exactly what parameters it takes. It knows what parameter it returns. Okay. So we'll just save that guy again. We'll try compiling it this way, like this. And I can just run it again and I get the same answer. Keep in mind that this little example here is totally useless if I put in let's say 2 to the power, well, let's say I put 2.5, oops, say 2.5 to the power of 2.5 to the power of 5. That should probably work. So 2.5 to the power of 5 is 97.656250. However, if I was to put y as a not whole number, then it would not work. So 2 to the power of 5.5 would not give me the correct answer. So, it's 2 to the power of 5.5 is 32. No, that's totally incorrect. And the reason, of course, is because when I go around this loop, I'm only going an integer number of times. I'm not going around 5.5 times. I'm going around exactly 5 times. So, we could put another comment in here and say only works when y is a whole number. So if we put y as 5.5, it's not going to give us the right answer. Okay, we'll close this window. I think that's a lot to absorb today. So we'll call it quits, and we'll see you for lesson number 5, hopefully very soon.